Welcome everyone. In this second part of the N-slit problem lecture, I'm going to describe what's called phasor. I'm going to discuss about phasor not because this thing is something that you are required to know at this point, but because it's such a nice thing to know in physics and engineering, and I hope you will agree with me that it's not a difficult thing to comprehend. And so if you listen to my lecture in the next 10 or 15 minutes, I hope you will agree that it's something that you can actually grasp pretty easily. Okay, so in order to understand why this concept arises, we go back to the question where this intensity comes from, and that came from total wave field, total electric field in the case of light, which can be written as in this form with sine of k x1 minus omega t plus phi plus sine of kx2 minus omega t plus phi all the way up to sine kxn minus omega t plus phi. So the thing that we need to do here is to sum up these signs. I already mentioned that an easy way to accomplish that is to use complex numbers. So let me actually at this point write down a very, very important mathematical formula, which is exponential I theta equals cosine theta plus I sine theta. Many of you will know this formula as Euler's formula. And if you actually ever if you never encountered this, well, here's your first encounter. This formula is so important. After you first lay your eyes on this, you should never forget it. And what is I here? I equals negative the square root of negative 1. And what is E here? E is a number which is 2.718 dun dun dun. And how is it defined? It's defined as limit of epsilon going to 0, 1 plus epsilon 1 over epsilon. So it's like this. If if the interest rate is 1% per year, and if you deposit $1, if you wait 100 years, it will become $2.718. That's basically the meaning of E. Okay, now using this Euler's formula, whenever you see sine or cosine, and when the going gets tough, what you do is convert sine or cosine to exponential I theta. And most often what you will discover is that the calculation becomes really, really easy. And then after your calculation is done, you can actually take its imaginary part to get the answer if you started with sine, or take the real part if you started from cosine. Here we got a bunch of signs, so we can understand these things as the imaginary part of exponential I of phases. So that's what we'll do. As a side note, in my written lecture note, I actually used cosines here, but by adding a constant phase to sine function or cosine function, you can go back and forth between sines and cosines freely. So don't be too alarmed if some authors use cosines, if some other authors use sines in this kind of expression. So anyway, this expression in the complex number form becomes a over r exponential I k x1 minus omega t plus phi plus exponential I k xn minus omega t plus phi. So what I did is just make this expression a complex number expression by replacing sine with exponential I theta. And the rule is, after you calculate this in the complex domain, you look at the imaginary part of the result, and imaginary part is I times something, and that something is your answer. Now let's look at this expression here. This expression, because the exponential function is basically a power law function, you can say that for example, you can factorize the first term here. You can factorize the first term here, and what is left inside the angular bracket here? Well, for the first term, of course, it's 1. For the second term, what we have is exponential I k x2 minus omega t plus phi. And what is the phase difference between the two? It's actually delta, because delta was defined as k parenthesis x2 minus x1. So that means when you go from the first exponential to the second exponential, the only difference is that phase increases by delta, where delta equals k x2 minus x1 equals k x3 minus x2, and so on and so forth, as we explained before. And what is the third term here? Third term is you go to exponential I k x2 minus omega x3 minus omega t plus phi. That's different from the second term by an additional phase delta. So that means this is becoming I times 2 delta, and so the pattern is quite clear. At the end, what we have is a I n minus 1 delta. So now what you do is you notice that this is just a geometric series, and you can sum it up, and you can express it nicely, and you write down the final answer, and you identify the imaginary part, and get rid of that I, and you will get that answer from that imaginary part. That's basically how I did it in my lecture note, except I used cosines here, so I was dealing with real parts in my lecture note. But that method is equivalent to what I just described. Here, I will actually not go through the detailed math. What I'm going to say, you can actually verify what I'm going to say by doing some simple calculations. What I'm going to say is true. It's a simple fact which is pretty useful to remember. What it is that this sum here, this simple geometrical series sum, let's say this is, let's define this f delta, because it's just a function of delta. This f delta is the only reason why we have this interesting interference pattern here. So this important function here The reason why that important function appears is because of this geometric series, and furthermore, the important expression is nothing else than the magnitude of f delta squared. So that's the important fact. That's the secret of the math that goes into the N-slit problem. Let me define each term here that goes into defining f delta as phasor. So this is one phasor. There's another phasor, and there's another phasor, and this is another phasor. So that's how I would define a phasor. In that sense, a phasor is just a complex number with magnitude 1. And some authors define phasors as a complex number with a certain phase and a constant magnitude. For example, A. Some authors decide to multiply A to all of these terms and define each complex number as phasor. But here, I do something equivalent, but I like a unit, complex number. I like the simplicity, so I'm going to define these complex numbers with magnitude 1 as my phasors. Okay, so remember one time I said that it's good to know the word phase, and here's the reason. Phasor is the complex number that carries the information on phase. And for instance, if you read many books written by Feynman, he would tell you that phasors are pretty much the only thing to know. So let's actually think about this problem in more detail. When we talk about exponential I theta equals cosine theta plus I sine theta, what we have here's the geometrical meaning of this Euler's formula. So here's angle theta and the length 1 vector. A complex plane is in an xy plane, a two-dimensional plane, and therefore the set of complex numbers is isomorphic to the set of two-dimensional vectors. So a complex number is a vector, and so this vector with length 1 and angle theta is what in complex number is called exponential I theta. It's as simple as that. And the real part of this complex number is cosine theta. That's the x component of that vector. And the imaginary part of that complex number is sine theta. And that's the y component of that vector. So there is that mapping between a two-dimensional vector and a complex number. So then, adding these complex numbers is equivalent to adding n vectors. All of them are unit magnitude, and you're basically adding them. So let me actually demonstrate this to you in the case of n equals 4, because that's a pretty simple case to examine. So let's say that n equals 4, and you start from delta equals 0. Okay. So delta equals 0. If delta equals 0, then all of these numbers, there are 4 numbers, 4 phasors, and all of these numbers are 1. So what that means is that when you add these phasors, when you add this. Let me actually use a reddish color for all the phasors. So this here is 0 and 1, and there are 4 of them. Okay, 4 of them. And so you will recognize that as delta equals 0 as the 0th order principal maximum condition. So remember, delta equals 2 pi n, 2 pi m. M is an integer. There was the condition for principal maxima. So m equals 0, delta equals 0. Of course, it's easy to see why the intensity is maximum there, because all of these 4 arrows are pointing in the same direction. If you add them up, what's the magnitude? Well, it's easy to say. So f delta is not even a complex number here. It's just 4. So that means this number becomes f delta square. It becomes 16. So that's why when n equals 4, when you plot f delta square is a function of delta, when this is 16. And then there's 2 pi. So remember what we did? We divided into 4 segments because n equals 4 and n equals to 0. So let's see why it becomes 0 there, the minimum condition. So that's 2 pi over 4. So delta equals, minimum condition is actually delta equals pi over 2. So let's plot the phasors here. It's more fun now. So the first phasor is always 1, so that's right here. Okay. The second one now is exponent I pi over 2. What that means is that length 1 vector with angle pi over 2, 90 degrees. So that's here. And then the third phasor is exponent I 2 delta. So that's pi. So that means angle is pi. It's right here. So you just add successively pi over 2 as you go to the next arrow. So you go there and you got 4 phasors. You're done. Now you ask the question, if I add all these vectors, what's the result? Well, that's pretty easy, isn't it? So this arrow cancels that arrow, and this arrow cancels that arrow, so that's 0. No wonder intensity is 0 there. Let's do another one. The next one here, so this is pi over 2, this is pi. So let's do another minimum. Delta equals pi. Delta equals pi is easy enough too. So what you do is you first start from phasor here. The second phasor is now rotated by pi. So there's there. And then another one here, because you rotate this phasor by pi, and then you come back to this again. So there are 2 phasors here. And there are 2 phasors there. So 2 and 2. It doesn't matter. Each of the 2 cancel, one another here. One of these cancel one of those, and so f delta in this case is also 0. You can see, right? So those are the reasons why the intensity is 0 at this intermediate. Points here, pi over 2, pi, and 3 pi over 2. So it's all 0. And then you get small blips here. That's not very good. And then it goes back to 16 when delta equals 2 pi, because 2 pi is equal to 0. 2 pi angle. Angle 2 pi is equivalent to angle 0. Now, let's consider the maximum here, which is approximately, not exactly, but approximately 90 in the middle between pi over 2 and pi over and pi. So that the average of pi over 2 and pi is 4. So delta equals so 3 pi over 4. So what happens there? So that's this small maximum there. Why that maximum is actually very small? In fact, this maximum is about 7% of that 16. And when n goes higher, the percentage height of this guy with respect to that principal maximum decreases. Okay, so let's draw this phasor here. So we start from length 1 vector here, and we need to go 3 pi over 4. So that's right here. Pi over 2 plus pi over 4. So this angle is the same as that angle, and that's pi over 4. And then if you go 3 pi over 4, then you will hit here. And then you rotate it by 3 pi over 4, then you will hit here. So if you add these 4 vectors, clearly it's not 0. It's not 0. But how big is the how large is it? So let's figure that out. If you if you add these 2 vectors, you can see that these are symmetrically positioned with respect to y-axis. So it'll be something like this. And that vector is actually this is 1 divided by square root of 2, so that this is square root. The length here is square root of 2 instead of 1. So, and this is length 1 vector. So when you add this green arrow to this other arrow pointing in the other direction, what you will end up with is actually a smaller arrow, because and because square root of 2 is about 1.4, this is about 0.4. So then the final sum of all the vectors is given by I'm running out of colors here, and let me use the white color here. So this one is not added up, was not added up yet. So when you add this vector to that vector, that's the vector. That's the final f delta. So in this case, you can see that f delta is not a real number. It's a complex number. It doesn't matter. What we need to do is we need to square it, take the magnitude and square it. So the magnitude here is actually 1 square plus 0.4 square, and then a square root of the whole thing. So the point here is that that magnitude is not very large. It's actually in the principal maximum case, the magnitude was 4, but here it's just a little bit over 1, right? So that's only 25% of this magnitude for the principal maximum, but the intensity is a square of that. So when you square it, f delta square becomes even smaller than this principal maximum case in terms of this in terms of the percentage. That's why these maxima that occur between principal maxima are very tiny. So that's it. That's the physics of N-slit problem or diffraction grading problem explained in terms of these phasors. And I hope you get some sense of this.